I'm Evan Chanin. So I manage the development of the FoundationDB key value store at Apple. And I'm going to spend the next 40 minutes taking you through the architecture of FoundationDB. I was first taken through the architecture 8 years ago. However, back then it existed as some hand-drawn diagrams on a piece of graph paper. What's pretty remarkable, though, is that it took around 3 years of development before we actually made any significant changes to the database that weren't on that original sketch. And a lot of what I'm going to talk about today, if you found that graph paper now, would be there. So it's pretty remarkable. So to focus this presentation a little bit, before I get into it, I wanted to highlight some of FoundationDB's strengths. So later, as I'm going through the architecture, I can kind of explain how FoundationDB is providing these properties. So one of the things is that FoundationDB is operationally very easy to use. And specifically, it does a lot for you in terms of load balancing traffic across the different machines in a cluster. And it also does a lot for self-healing in response to failures. So I'll come back to both of those points as I'm going through the architecture for how we do it. The other point comes back to something Ben really mentioned, which is that we provide scalability without sacrificing performance or consistency. It's really easy to be skeptical about a claim like that because it sounds too good to be true. So I want to be really specific about what we mean about this, and so hopefully I can convince you all that we actually do it. So it's a little bit easier to talk about not giving up consistency in FoundationDB for scalability. FoundationDB gives you ACID transactions. There's a single global key space. Inside of these transactions, you can read or write any key across the whole database. FoundationDB gives you strict serializability and external consistency, which I'll get into a little bit later. It's a little bit harder to quantify what it means to not sacrifice performance for scalability, because there's a lot of dimensions to performance. So my approach is to think about FoundationDB as organizing a lot of individual, non-scalable key value stores into a single cohesive unit. So we can talk about the theoretical perfect performance of a system as if you dedicated all of your hardware to these individual key value stores. What would be the aggregate throughput of all of these things put together? What would be? And so when we compare FoundationDB against that model, we achieve roughly 90% of that theoretical best perfect scalability. And hopefully I'll be able to convince you of that as we're going through it. In terms of latencies, our read latencies are basically as good as you could possibly get. They're a single hop from a client directly to a server that's going to serve the response for that read. Writes are a little bit worse. To get a write successfully committed to the database, it's about 4 hops through the system. In practice, this is going to mean about 4 or 5 milliseconds of latency on commits. So it's important to note that all of this argument about performance is related to the architecture, which is what I'm going through. But it says nothing about our actual performance. And in fact, a lot of the projects we're working on today are going to significantly improve the performance of our system as a whole, like the Redwood storage engine. So, but this is basically showing us with a perfect implementation of FoundationDB, the sky's the limit. So now I'm finally ready to get into it. And I'm going to do that by starting with a little bit of distributed databases 101. So in this diagram, we have 3 servers and a single writer, which is trying to push data into the system, and a single reader, which is trying to get data out of the system. And in this system, we have the criteria that we need to be resilient to a failure of a machine. So the traditional way to do this is using quorum logic. So if the writer, when it's writing data, makes sure the data gets to 2 of the 3 servers, and the reader reads from all of the locations and only only successfully reads when it can talk to 2 of the 3 servers. We'll make sure every piece of data gets to the system. And then if one of the servers fails, well, the system will just keep going on naturally because we only needed 2 out of 3 responses from both places. Basically, this system has implicit failure handling. It just will naturally and gracefully handle failures. So kind of the, I guess I should have brought some water up here. So sort of the core principle behind FoundationDB is if we don't actually need this implicit failure handling that I just described, there's actually a lot of benefit we can gain by doing things slightly differently. So in this case, since we don't have to handle failures, our writer can write to all 3 of the servers. Because we now know, well, thank you, Ben. You're rescuing me from my cough. Okay. So if the writer writes to all 3 of the locations, this actually gives us 2 huge performance wins. One of them is obvious, and the other one is a little more subtle. So the obvious one is because the data is now at all of the servers, the reader no longer has to talk to all the servers to do a read. It can actually go to just one of the servers to get a response because they all have all of the data. There's no like quorum to combine them. So basically, our reader is now 3 times more efficient than it was in the previous diagram. The other more subtle point is that when we can handle failures in this system, we're actually going to do a lot better job. So the quorum logic with 3 servers gave us a resilience of a loss of this one single machine. In this system, because the data is making it to all 3 servers, we actually can lose 2 of our 3 servers and not lose any data. So we're going to be much more resilient to failures. So then the question obviously becomes, well, how do you handle failures? And so the FoundationDB answer to this, and kind of one of the key innovations behind the design, is that we are going to have an entirely different database that is going to store metadata about this other database, about our primary database. And so basically, this other metadata database is going to hold membership of the servers that are in our primary database. So in this case, the servers A, B, and C were responsible for committing data at version 0 when we started up the database. And at some point in time, server A died. And then we replaced server A with server D. And so we wrote to this other database. Now we're doing our commits to B, C, and D. This other database can use the quorum logic and implicit failure handling that we talked about before. And because it's a very low traffic database, you're only gonna ever write to this other database when there's failures in our primary database. So FoundationDB took this basic idea and turned it into a system. And so now I'll start adding boxes. So this diagram here shows all of the stateful components of FoundationDB. So the coordinators are this other database I talked about, this metadata database that uses Paxos and quorum logic to do its writes. And a fun trivia fact, the first version of FoundationDB, this literally was a separate database. We used Apache Zookeeper to hold this metadata, and which was quickly replaced with our own implementation, like a year later. So for the other stateful systems, we have the transaction logs. And this is a distributed write-ahead log that's responsible basically for accepting commits and writes into the system. Its job is basically to get stuff durable on disk as fast as possible so that we can return a commit successfully to the client. Basically, it's a write once, read never data structure. Mutations are only being held there transiently. They're coming in. We're making them, appending them to the end of the file. And then once the storage servers have the data, we'll quickly get rid of it. So generally, they're using very little storage. They're also super efficient because they have such a simple job. The storage servers go back to the point I was making when I was talking about performance and scalability. So they are 90% of our system, and they are all basically individual key value stores that we're kind of allowing to cooperate together to act as one single big key value store. So each one of them, is basically holding data for long-term storage that it's getting from the transaction logs, and it's serving read requests that are coming in from the users. basically, the entire system is designed around making these guys' job as easy as possible and to simplify that. So because they're the bulk of the system, the transaction logs basically are set up in such a way to make the storage servers have to do as little as possible when they're ingesting writes. Like the clients and how we're doing our reads are also trying to do as few reads as possible and balance load for them. So to that end, when the transaction logs are sending data to the storage servers, the way we do this is we have every storage server has a buddy transaction log. And that storage server is going to get all of the data that it's responsible for from that one location. So basically, it's getting an exact stream of writes that are specifically designated to this one specific location. And so we'll talk a little bit about how that happens, but we're doing it for efficiency's sake. Because these storage servers are only talking to one other server, it's super efficient. So now we can start from here and start adding on the stateless components onto the system. And the first one I'll talk about is the cluster controller. So the cluster controller is a leader that's elected by the coordinators. And its job is basically to organize all of the processes in the cluster into the full system. So basically, when every process starts up, it's going to talk to the coordinators to figure out who the cluster controller is. And then it's going to register itself and kind of whatever information it knows about the process to that cluster controller. So it's going to say, I have a disk. I prefer to be a storage server, and this is my information. So the cluster controller is then going to take all of the workers that have registered with the system, and it's going to start assigning them to do these different roles. Well, you become a transaction log. You become a storage server. The cluster controller, in addition to giving out roles, is also doing failure monitoring. So it's going to track. It's going to be basically talking to these processes continually to determine if they fail, and we'll get into failures a little bit later. So before I can add more boxes, and trust me, there's more boxes, we have to take a little break to talk a little bit about how FoundationDB provides consistency. So I mentioned strict serializability before. And so to provide that, we first need serializability. And in FoundationDB, serializability is explicit. Every single commit you do is given a version number. And you can just observe the serializability by comparing version numbers. You know this commit committed after the other one or happened after another one if its commit version was higher. So it's right there for you to see. It gets a little bit more complicated when you want strict serializability. And basically what we need to do here is make it so that when we commit, it's like our whole transaction happened at the instantaneous moment in time that the transaction was committed. And the FoundationDB approach here is basically when you start a transaction, you get a read version, which is basically the latest commit version of that the system has committed previously. Once you have that version, for the rest of your transaction, all your reads are stuck at that moment in time in the past for when you started your transaction. And so the data you're reading from the database is going to be, a little bit old. It's not going to see the newer stuff that's going to come in. It's just stuck at that consistent point in time. And then when you finally go to write, the whole concept here is that if none of the keys that you read changed in this time interval between when you started your transaction and when you eventually committed, then it's actually like you did it's actually like you did all your reads at the final commit version. It's like you're at an instantaneous point in time. So that's the optimistic concurrency model of FoundationDB. And as a consequence, if someone changes one of the keys you read in this time interval, in this short window between your read version and your commit version, we fail your transaction as a client you retry. The layers team, is kind of having to deal a lot, and you're going to hear a talk later by Alec that this is something that you have to be very conscious of that happens in FoundationDB, and you have to work around it. Okay. Back to the boxes. We now have an API, and you can see that there's now a master and proxies and resolvers added to the diagram. And these components are all basically these stateless components that are here to implement basically the consistency model I just described. So let's go through the different operations you can do on FoundationDB and see what happens. So we'll start in with reads. As mentioned, reads are going directly to the storage servers that are responsible for those range of keys. So if you read key A, there's going to be some set, if you're triple replicated, there's going to be some set of 3 servers in the system that have that data, and you're going to talk directly to one of those servers, and the storage server is just going to give you an answer. If you remember from the previous slide, your reads are versioned, right? So you're passing in a read version with your thing, and the storage server has to give you the value of that key at that moment in time. So we're reading A at version 200, and the storage server basically is going to keep some history in memory of recent commits, and it'll give us A at that version. This comes back to one of kind of the constraints of FoundationDB that you probably already all know about, which is the 5-second transaction limit. There's 2 places I'll mention the 5-second limit. One of them is right here. Because currently the storage server is keeping the recent history in memory. And so to limit the amount of memory used by the storage servers, we restrict like how much history we keep. So we only keep 5 seconds. So the other thing to mention here is this metadata related to which storage servers have which keys. Because as a client, you need to know who to talk to give you an answer to any individual query. So this like mapping between keys and the storage servers responsible for them is state that's actually held in a lot of components in the system. The client keeps a cache of these locations, and if it doesn't have an answer, if it doesn't know at any given moment who's responsible for keys, it's going to ask the proxy for that information. So the proxy keeps the entire map, and the client will just send a request over the proxy saying who is responsible for key A. If we shift responsibility of a shard, the client's cache could be invalidated because the person it previously thought was responsible for the keys is now shifted. And in that case, the storage server itself will tell the client that the data is moved. The client will invalidate its cache, and it'll re-grab the answer from the proxy to get the correct location. This state, this mapping, is actually stored in the database itself. And what's kind of a really cool and interesting design, so it's the FoundationDB, the byte FF is the system key prefix, and it stores system metadata in the database there. And to change shard responsibility to give ownership of a key range from one set of servers to another, we actually accomplish this by just committing transactions to the database itself. So it's a 2-phase protocol where you say, like, I'm intending to move this range to some other location, and then once that location has copied all the data, then you do another one saying these servers are taking over responsibility. So this data distribution algorithm is responsible for a lot of the load balancing that I was mentioning earlier that we get out of FoundationDB. So basically, we're constantly kind of monitoring how much work each of the different storage servers are doing and shifting responsibility around by executing transactions on the database, kind of giving ownership of keys. So like if you added a completely empty new process to a FoundationDB cluster, what's going to happen is the data distribution algorithm is going to notice there's now a new process in the system, and it'll just start giving it key ranges and key ranges until it's like taking some traffic. Okay, a lot on reads. We're on to commits. So writes in FoundationDB are actually just cached up on clients, so there's nothing really to talk about there. And commits are basically going to take everything you did in your transaction, bundle them up together, and send them as a single unit to one of the proxies. So in this case, you're gonna include the version that you did your reads at, every key that you read, and then every mutation you're attempting to write, and package that up together. And the very first thing the proxy is going to do with that information is assign that transaction a commit version. So in this case, we did our reads at 200, and the master is going to tell us that we're committing at 400. So the master's job, it's the only singleton in the pipeline that's not scaled out. There's only a single box here. And its entire job is just to give larger and larger commit versions back to the user. Even though it's a singleton, it'll never be a scalability limit to a cluster. because it has such a simple job, and as you scale up the system, we actually combine different transactions together into batches, and the master is only giving a single version number to an entire batch of transactions. So basically, even if you hammer the database super hard, the master is not really going to sweat giving out these version numbers. So once you have a commit version, you're now ready to do what I was saying on the previous slide, and detect to see if anything you read in this transaction changed between your read version and your commit version. And that is being done on the resolvers. So basically, this is another location where we get back to the 5-second transaction limit, because the resolvers are a stateless role that are storing the previous 5 seconds of history of reads and commits, or reads and writes, and it will basically be able to tell you for any given read if it's changed in a time range. So one important thing to note about resolvers is they're sharded by, when you add multiple of them, they're sharded by key range, and so you're going to split up your reads and writes according to the key ranges of those resolvers and send just the specific data for those that resolver is responsible for to those locations. What this means, though, is that as you add more and more resolvers to a system, you're doing a little bit of conflict amplification. Basically, the two resolvers don't know about the decisions the resolvers don't know about the decisions other resolvers are making. So if one of the resolvers fails a transaction and the other thinks it succeeds, well, the transaction was failed, but the one that thought it was successful is going to fail future transactions based on the writes that happened in that one, even though they didn't actually apply to the database. In general, this is not a huge issue, and FoundationDB, as I've mentioned already, you already have to design your clients to avoid high contention workloads that are doing a lot of conflicts anyways. But in general, it means that you don't really want to scale out resolvers. You don't want to just configure 100 of them right off the bat. Start slow and scale up to just as many as you need. So assuming the resolvers haven't found any problems, we can now finally make the transaction durable. So the proxy is now going to ship the mutations, the writes from this transaction to the transaction logs. And so as mentioned previously, every transaction log or every storage server has exactly one transaction log that it's going to get all its data from. So if we're writing key B here, there's some team of storage servers at the end of this pipeline that need that mutation that changes key B. And so those servers are mapped to some transaction logs. And so the proxy basically knows all these mappings, and it's going to send the change to key B to the set of transaction logs that'll eventually get the data over to the storage servers responsible for it. Because there's way less transaction logs than there are storage servers, you could just happen to get lucky or unlucky that all of the locations that want key B are just one transaction log. And in that case, we actually have to additionally replicate key B onto some other transaction logs so that we're safe against failures in the transaction logging subsystem. So there's a little bit of complicated logic the proxy does to figure out where to store the mutations in the transaction subsystem. Once the data has been f-synced on those transaction logs and made durable there, we finally can return success back to the user, and behind the scenes, the data is going to be replicated over to the storage servers. So finally, I can wrap all the way back around to a get read version request. And get read version requests are responsible for giving us, or how we provide them, are responsible for how we provide external consistency. So the concept here is that when you start a transaction, it's a very nice property that you'll see every commit that's ever previously happened on the system. So in this specific example, like we previously committed to one of the proxies, and now if we immediately start another transaction that talks to a different proxy, we want to make sure that this new transaction sees the result of the previous one we just did. So the way we do this is that when we talk to one of the proxies for a read version, that proxy will send a message to the other proxies asking if they've seen any versions that are higher than the one we have locally, and we'll just take a max of all those responses and send it back to the client. This may at first glance seem like a scalability problem because every proxy is basically talking to every other proxy exchanging these versions. However, we're saved here by batching. We basically can we don't have to do these reversion requests for every single transaction. We can group up a lot of different requests together, and for a whole bunch of them, we can send these requests to the other proxies. So really, we're only sending these messages between proxies every millisecond or so. Okay, so that's kind of that's the first part. We've gotten through how you how you do commit how transactions flow in FoundationDB. However, if we wrap all the way back to what I originally said, a huge part of this design that we've a trade-off that we've made is in relation to failures. So basically, we're having to explicitly handle like failures in FoundationDB because we don't have the implicit failure handling that quorums give you. So now I'm going to take you a little bit through what happens when a process fails in FoundationDB. So I'm going to start with the hardest one in this case, in which case a transaction log dies. And so this is going to kick off a recovery process. So the cluster controller is going to detect that this server has gone down, and the first thing it's going to do is basically attempt to recruit an entire replacement for the entire transaction subsystem that's going to basically take over from the previous generation. Basically, like storing the data in this other coordination database, on the coordinators. So this is using this write is going to use Paxos, and we're doing this because it would be an absolute disaster if we could have two different masters take over simultaneously. Like any consistent system is going to need a two-phase commit somewhere. So the first step is the first phase of our two-phase commit, where we're going to do a read from the coordinators to find out who exactly were the transaction logs of the previous system. This new master is then going to talk to those old transaction logs and find out the final version that was committed to them. In this case, the one that died had version 400, and the other ones that were alive actually got another commit after that. There's 410 and 420, so they have even more recent data. Because the commits had to go to every single log, the only version here that actually was returned commit success back to a client would have only been version 400. And so, but we're allowed to take any version after that. So 410 or 420 is also fine. It's sort of like a client, it doesn't know the result of those transactions. So the master so when it's asking for these versions, the master is also locking these transaction logs to prevent them from accepting any additional writes in the future, basically preventing us from recruiting new logs and having the old logs continue accepting writes. And the next, so the master is then going to pick kind of the lowest of the responses it gets back from these guys, and take that and basically tell the next generation that they're taking ownership of the database starting at that moment. So the master is then going to basically start up all of the other systems at that moment in time. So the proxies are going to recover that key to serverlet mapping as of that version. And the transaction logs actually have to do a little bit of copying as well. And the reason for that is actually really subtle. So back on the previous step, I said that we see that this transaction log with version 400 is dead, is gone, right? But that might actually just be a temporary failure. It could just be a little network hiccup that triggered this recovery. And if we have three servers and we're triple replicated, we actually want to be safe against two failures. So what can happen here is that after we've committed to a recovery version of 410, the two remaining guys who are alive can permanently fail, and this one guy who was temporarily dead at the start can come back alive. And this guy only has version 400. So we need to copy just a little bit of data from the previous generation to make sure that even if there's this crazy scenario of things dying and coming back alive, we're still able to have all of the data up to the version that we committed to be our recovery version. In any case, once the transactions logs got this little bit of data, we're finally ready to go with this next generation. So the master is then going to do the next phase of the two-phase commit to the coordinators, kind of finally writing these new sets of transaction logs into the database, saying that they're taking ownership from the previous generation. After all of that's happened, we can finally tell the cluster controller we've taken over, which can then basically open the floodgates of traffic onto the system again. So that was the hard one. If that same recovery process I just went through is going to happen even if a master, resolver, or proxy dies. The philosophy here is basically we know we have to make this one recovery algorithm really fast. And so if we do the hard case really well, we can just use that hard case to handle any failures, even if they're potentially a little easier. So eventually, we may get around to writing specialized recovery logic for replacing some of these stateless roles. But for now, there's just one process that happens if any of them die. If the cluster controller dies, well, that's really simple. It's a leader elected by the coordinators. And so it's heart beating constantly to those coordinators. And so when it dies, it'll stop heart beating, and the coordinators will detect that and just elect a replacement. And even simpler than that, if a coordinator dies, well, it's using quorum logic. It has implicit failure handling. Nothing happens when it dies. The user will probably want to replace it just to restore fault tolerance, but there's no emergency. And finally, we wrap down back over to the storage servers, which, as you can recall, are 90% of our processes in the system. And when one of these things dies, there's basically no effect to the user. Clients will just automatically start sending requests to the other remaining servers that are responsible for the keys that server had. And that data distribution algorithm I mentioned earlier is going to start shifting the responsibility of all those key ranges on the failed node to other sets of alive servers. So the system will just naturally heal from this problem with no problem. So that's kind of the gist of it. I just have a few other points to talk about. One of them is kind of a performance pathology that's specific just to FoundationDB, really. So as I've been talking this whole time, we've mentioned a number of times this 5-second transaction limit. And normally databases handle saturation performance by basically relying on back pressure so as more and more people overload a server, it'll just naturally slow down the responses to those requests. However, in FoundationDB, because of our 5-second limit, that can lead to a death spiral. The concept is like if every read you're doing, if you're doing like 5 or 10 serial reads in a row in your transaction, if every read starts taking a second, well, all of a sudden, by the time you get to your last read, you've passed the 5-second limit. So then you've done all of this work and all of these reads, and you get to the end and you try and commit and you just fail. And if every client starts doing this, then basically no work is being done in the cluster. It's just a disaster. You're in a death spiral. Everyone's hammering the servers, and no work is getting done. So we saw this problem, and our solution to it was this concept of rate keeper. The idea is that when we're in saturation, we're going to build up all of the latency before we get the original read version to our request. So basically, back to the diagram, when you start a transaction, your 5-second limit really only starts from the moment you get a read version. Basically, you have to commit within 5 seconds of getting that version. So if we can basically slow down the rate at which the clients are getting versions, we can make it so that even though it might take a few seconds to get a read version, once they have one, they'll be able to do all the rest of their operations with very low latency. So that rate keeper component is another singleton that lives on the master. So the final thing to mention is sort of a theme of FoundationDB, and Ben highlighted it a little bit. But as you know, obviously this design is really complicated. There's a lot of little moving pieces there, and there's a lot of edge cases I didn't even really get into in this architecture discussion. So the question of the day comes back to, well, how can we trust, or how can you guys trust that we actually don't have any bugs that just throw out this entire design? Like, you don't actually have ACID guarantees if there's some bug that corrupts your data in some weird case. So basically, the founders recognized this basically from the get-go, and that's why they started with simulation, right? Because the idea is this thing needs to be tested really severely so that we can actually trust that our implementation of this design is meeting the guarantees we say it does. So the way this works is kind of when I was going through this whole architecture, right, I was talking about all of these different processes and these boxes sort of in my mind and maybe in your mind. You're thinking about them as happening on different machines or different processes in those machines. But in actuality, there's an indirection between the roles in the work that's happening and where it's happening in the cluster. So it's actually, you can actually start up a FoundationDB like cluster on your laptop in a single process, and that one process will do all of the work of all of these roles right there locally in that one process. What this allows us to do is, if when we're running the whole system in one process, we can actually have that single process pretend like it's an entire network. So it could, because it's all one process, just instantly send messages, from the proxy to the resolver, from the resolvers, back to the proxy, from the proxy to the transaction log. But instead of doing this instantaneously, we actually pretend like there's latency between these components. We drop some packets randomly. We reorder things. We pretend like whole system dies. We pretend like there's corruption on disk. Basically, every bad thing you could possibly think of, we do in this system. And because it's a single process that's doing this, we have determinism. So if we can run, we run hundreds of thousands of these things, of these randomized tests every night, pairing these random failures with some workload that's going to check some property of the database. And when it comes back with an error, we can, in the next morning, replay the exact really rare series of events that caused this and kind of figure out what happened. This is really powerful. Of my 8 years working on this database, probably 6 of them has been spent tracking down problems found by this thing. It's really kind of one of the big secrets, sauces that makes FoundationDB possible. So that's all I have for you guys. Before I step down, I just want to say thank you to Dave Rosenthal and Dave Shearer. They made a lot of hard decisions early on with developing the simulator, developing Flow, even through developing this whole architecture. Basically, at every moment, they were making technical decisions early on. They were focused on kind of the long-term sustainability or long-term success of this database. And so now I'm reaping the benefits of the work they laid out early on. So thank you, guys.